Well, thanks for joining us today, Professor Bregman. I wanted to start this podcast episode by talking about space policy. And so with kind of the transition from the previous administration to the new Biden administration, there's a lot of change that goes on, whether that be policy in terms of where the funding goes, or also more specifically, in our case with this podcast, science funding, or in your case, astrophysics and astronomy funding. And so we wanted to talk a little bit about concerns or possible concerns that scientists may have in this transitional period. Is this a time for you as an astronomer to be worried about where the money's going and how the money's changing? Or in general, does science kind of, is science not affected by the 4-year turnover between administrations?
Well, it's a great issue, and I'm always concerned about where funding is coming from and what our priorities are. The administrations have often found that science is really bipartisan, but there have been some differences. One of the big changes in during the Trump administration is how the budget progressed. So, for example, the usual thing was that the president would make up a budget after consultation with the budget office and science priorities and their own science office, and then they would send it to Congress. Congress officially is the one who makes the budget. But usually the budget was close enough, say an Obama budget, that they started working from that. And they would take some stuff out or add some things. In this case, the Trump budgets were so violently different from what had come the year before that Congress just ignored them. So by doing that, instead of having this play between the executive branch and Congress, the executive branch took themselves out of the equation. And it just became the Congress who decided where the funding would go. And of course, the Senate and House sides come up with slightly different answers, and then they meet and have a final reckoning. And excuse me, so now we're back to the way things used to be. That'll really start again next year because these budget processes take about a year to turn over. And what we're hoping is that, so the difference between Democratic and Republican administrations is that the Republican administration will tend to put more money into R&D in the military, somewhat at the expense of basic research, while the Democrats will tend to put more money into applied physics and applied programs at the expense of basic research, usually. So we're always fighting that battle for basic research. It's I think that it has such a long time scale between basic research and products appearing on shelves that it doesn't seem to have the urgency of finding a cure for cancer or something like that.
And just as kind of a refresher for the audience, in case they're not familiar with what applied research would be versus basic research, would basic research just be, for example, astronomy, studying something where you don't know what the eventual implications would be, or studying something just for the pursuit of trying to know what it is or why it does what it does, whereas applied, you have kind of a end goal to be applied to somewhere in society for medical reasons?
Right. So, for example, curiosity-driven science or curiosity-driven research is considered basic research. And when it's being done, it often doesn't appear that it will have an application, and maybe it shouldn't. We should be driven by curiosity. But for example, when people were working on nuclear physics about over 100 years ago, people asked the leaders in that field whether or not it would have any applications, and they said none at all. So they got that wrong. And there have been some research in mathematics that seems so esoteric that it's hard to see that it will ever become part of anyone's life. But then, 20 years later, you find it does. So those are that, astronomy, those are our basic research. They train scientists, and they lead to lots of interesting results. Applied research might be something support, say, in the engineering school to improve solar cells or batteries. And that has obvious implications, immediate or soon. And because that has more appeal, at least to some of the legislators who are in control of funding. So there's always a bit of a challenge to protect basic research.
And how do people involved in basic research make sure that people will continue funding it? Because it is probably true that it's not particularly appealing to people who actually hand out the money to be investigating something that's far out in the sky. People don't see its immediate impact. So how do people involved in basic research make sure that that doesn't just go away? Is because it seems to me that some people accept that basic research is important, and so they'll continue trying to, and so they'll continue to try to keep it in the budgets. But at the end of the day, it seems like basic research is one of the easiest things to cut, because I think a lot of people will say, well, there's not too much impact here, so if we need to save on some money, basic research would be a good thing to cut. So how are scientists making sure that that isn't the case?
Okay, so this leads to the general question that if you were a congressman, you would ask also, which is, we spend a lot of money on this stuff. Is it going to the highest priority things? And the way we solve those problems are twofold. It's we have a peer review process to evaluate what are the most important things to do. But as a field, we do it every decade. That is, every decade we look over the whole field, and it's a process that's just wrapping up right now. The report will be out this June. And they say, well, what are the big things that will happen this decade in astronomy? What are the new facilities that would lead to great discoveries? So there are a number. So this sort of thing was first done actually by astronomers in the late 1950s. And Congress liked it so much that they now make essentially all science areas, physics and biology and chemistry, do the same thing. And they love it because then they get this document that says, here are the priorities. This is what we should be doing. This is what we think are the areas of the biggest science breakthroughs for the coming decade. And these are the sorts of new facilities that we need to be building. So that's going on. Then there are somewhat the meta questions, which is how much should a country be spending on research and development in general, and basic research in particular in this case. And they've had a number of commissions that have looked at this, and they all have come back with the same answer, that we used to spend more than anyone else on things, but that has been dropping. And so the funds for basic research in real dollars have been flat or actually have decreased a little in the last 8 years or so, 10 years. And the recommendations by all of these commissions, which include industry and military figures, is to devote more money to research and basic research as well.
And so what kind of objectives do you think that the 2020 or 2021 Decadal Survey will set for astronomy? Do they typically pick one big sort of area of focus and then just exploit and try to exploit it as much as possible? Or is it typically a rebalancing between the different fields within astronomy?
Well, they'll look and see what they think the most important issues are and whether or not progress is possible. So I think one of the really important issues is, are there many, many universes? Are there multiverses out there? It's a great issue, but there's just no hope of observationally addressing it. So it has to be that overlap in the Venn diagram between exciting and possible. So NASA has 3 big questions that they like to raise that are some of their guiding principles. And it's not too different in the National Science Foundation or Department of Energy. One of them is, are we alone? What are the, what's the landscape of exoplanets? Is there life on other worlds? Things like that. How do exoplanets form? So exoplanets are planets beyond the solar system. Another is, how did the universe come to be the way it is? So starting from the Big Bang early on, evolving to the way it is today, is a big area of study. And one way of studying this is to look back in time, which means looking to fainter and more distant objects. Another area is, how does the universe work? And for example, how do stars blow up as supernovae? What is the nature of black holes and their environment? How do they come to be? We have a supermassive black hole in the center of the Milky Way, and essentially every big galaxy we know about. How did that happen? So there are these meta questions, and those are the ones that get all the attention. And it's somewhat quite natural, because if you took a problem that was really more of a problem in the 1950s and said, we can improve upon this, and it'll lead to a little bit of an improvement in our understanding, but wouldn't that be nice to do? The answer would come back roaringly, no, not really. So there are these areas that, and there's more than one area. There are these areas in astronomy and astrophysics that look like they're great places for future development. So, for example, and it's, how do you balance gravity waves from inspiraling black holes with the atmospheres of exoplanets? It's very hard to choose one over the other, and there's no need to. There are enough people doing different things, and if you want to be relevant on the world stage, you have to do many of them. So that's, but then comes the question of, what's the next big facility that you should build? And that's a harder issue, because there are some areas that aren't technologically well enough developed. So, for example, the next generation, we've done a lot of work on exoplanets. The next generation telescope that will actually image exoplanets and do a lot of them is a very challenging and very expensive program. and maybe in a few years it will be less so.
And how do those big projects get organized? Because it seems to me that, if you have a stack of money, you can either hand it out to, some scientists who are just, to pay for their labor and their housing and their food, or you can spend it by building something. And there are some really, really big projects like we've seen the LIGO observatories, the James Webb. Who's planning them at the initiative? Who's sort of driving those projects together? Does that come from the government saying, well, we'll give you a certain amount of money for large projects, and then an organization like NASA then is going to decide to do which big project they're going to do? Or is it individual scientists from universities who put together proposals, and then the best proposals get evaluated? It seems like it's a generally pretty complicated process to get the money and the scientists and the interest all lined up at once. So how do people go about doing that?
Right. So in the bad old days, before we had these decadal surveys, say if you were in physics, you would get a few physics Nobel Prize winners together who would then accrete a large army of people, and you would argue for a next generation collider or something like that. And the way it works now is more through this decadal process. And you not only want the good ideas, you want to know how much it's going to cost. So for example, and as you say, what should Congress pay for? Where should research funds go? You want a balance. You find that to make good progress, you need a balanced program. You need small, medium, and large missions. You need the scientists funded to analyze the data that come in. You need all of those things. The small missions, those are simply open to proposing. So there's an announcement of opportunity that comes from, say, NASA or the National Science Foundation, saying that we're open to building explorers this year. And the price cap is such and such. Send in your proposals by, December. There is one December this year that I'm involved in. Then 25 proposals go in. It's a tremendous amount of work because you not only have to explain the scientific goals, the observations that you will obtain to get them, but also the instrument that you will build and the cost estimate for it. Okay. And so you have an army of people doing this. And then it's evaluated by a group of your peers, and I've been on these committees, and they look through, say, the 20 proposals will go to 3 different committees based on the field areas, and they'll evaluate them and rank order them, and then they'll merge them together and they'll discuss what are the top ones. And then the NASA official makes the final call as to which is going to be chosen or which will be advanced to further design. So in astronomy, they will usually advance something for these missions, the Explorer missions, which are $150 to $300 million. They'll advance them to the next design level. Let's say you 3 have been chosen, and here's $1 million to do your work for the next year and come up with a more detailed design and work out the problems. And then we're going to ask a lot of hard questions and make a selection. So that's how that goes. However, the really big things, what we used to call flagships, now called large strategic missions like JWST, those are driven from the once again, there may be a group of individuals, but they know that the Decadal Survey has identified something or other as being a great area for future development. And then in preparation for the next big review, in this case, the next big Decadal Survey, NASA provided a fair amount of funds for 4 different flagship missions. And so those are, $4 to $10 billion. And they're really expensive. And then they also provide development funds for a dozen probe class missions, which are about $1 billion. And those will be reviewed. Both of those will be reviewed by the Decadal Survey. They'll say, here are the pros and cons, and then they will make a recommendation. They say, we think that da-da-da should be built, and development funds should be provided for such and such, and away you go. And then you have a list of the top 3 things that big ticket items that the field is asking for, that you can then present to Congress and argue your case. And they're very receptive to it. I mean, everyone likes astronomy, so it's not a hard sell when you walk up to the Hill and talk to people.
And one issue I see with flagship missions is, at least when I think of them, I think of the James Webb or maybe Hubble, and they always go over cost, or there's some kind of issue. So in Hubble's case,
Yes.
It wasn't working originally, and they had to spend a lot of more money to send astronauts to fix it. Or with the James Webb, it was supposed to launch a while ago. And so,
Right.
How does Congress take into account missions that are, halfway complete, 3/4 complete, that are way over budget? Are there any cases where they'll cancel them completely, or wait for a new administration to come and kind of revamp it? Or for the most part, do they finish and have to eat away the budget in some other area of astrophysics or basic research because it went over budget?
Yeah, it's the latter thing that usually happens. So they get very angry, or they get angry and then they get very angry. So Hubble also had a come to Jesus moment, as did the Webb telescope. And so they threaten that they're going to, stop it, or they're going to throw off the least important instrument and things like that. I've seen it with every mission that's, $1 billion or more. And sometimes what they'll do is they'll get, very angry. They'll work with NASA and the teams to restructure the budget to something that actually, although expensive, makes sense. And that's what they did with the Webb telescope. Then when a smaller program, what we call Small Explorer, was running over budget by about 20%, they showed they meant business and they canceled it. So they canceled that because the Webb telescope ran over. And when one of these big things has problems, everyone has doubts that you can actually build these big things. So there were 3 big things that were all in some trouble at about the same point in the 30 years ago, and that was the space station, which was the most expensive, the superconducting super collider, which was the next one, and Hubble. And the fact that Hubble had this terrible problem, I contributed to it wasn't the leading cause, it contributed to the cancellation of the superconducting super collider, which was under budget by about a factor of 2, and everyone knew it. And I think that's a case where Congress got so pissed off at them that they just canceled it. So
that was the one located in Texas, right?
Right, right. So it can happen, but generally what they'll do is they'll continue building it, and they'll take the money from things they were going to do. So there's a big cost that you pay. We used to have twice as many explorers going up as we do now, and they did that cut to pay for, overruns of not just a JWST, but there were other things. So that then leads to a couple of questions, which was, do you need flagships, these really big things? And if you do, is there any way of keeping the costs within bounds? And I think there is. So there are things you can do with small missions, small sats, $20 million, you can do things. But if you're going to probe if you're going to image planets around other stars and probe the outer reaches of the universe, you just need big glass in space. And that's going to cost you. So there are things where you absolutely need flagships. And so the way that you keep costs in line is you do a lot of engineering to get a cost and to get a budget. And then when you do that, you can keep things much closer to being in line. And over the last half dozen years, NASA has done that. So the cost overruns. I mean, JWST started in 2000, and the way it started was the head of NASA, who was a little bit crazy, Dan Golden, said that he wanted a successor to Hubble, which was at that point doing great. And they said, okay, well, instead of a 2.4 meter, we'll build a 4 meter in space. We knew we could build a 4 meter telescope in space. And he got extremely angry. And he says, do I have to do all the thinking for you? It should be not 4 meters, it should be 20 meters. And you should build it for under $1 billion. And so, that started the ball rolling. And then at some point, I think they started off with 8-meter mirrors, and they really realized at some point that they could not possibly afford to build that. And then it went down to 6.5 meters, which was the current size, which they thought they could build. But there were a lot of technical challenges. You need to keep the telescope cool, and so you put a shade in front of it. And this shade that is a 5-layer shade is the size of a tennis court. And no one's ever built that to deploy in space. And that was a big part of the problem. Early in the days, these beryllium mirrors were cracking. And so there were, this is somewhere you can say we did think boldly in building JWST. It is a very ambitious project.
And there seem to be a lot of issues that come up with, these 21-year spanning missions like the James Webb, where originally you have these scientific goals in the year 2000, given your current understanding of how the universe operates in the year 2000. Then all of a sudden in 2020 or 2021, our understanding of how the universe works, we've made so many discoveries between now and then, whether it be about the universe or whether it be actual technology. And so how does, a flagship mission spanning that many decades kind of keep up with the progress of technology? Or does a lot of the science involved on the James Webb, is it kind of based off of, things in the early 2000s?
No. So the only reason you do something in space is because you really cannot do it from the ground. Mm-hmm. So X-ray astronomy, the atmosphere absorbs X-rays and UV light. And far infrared light. So you have to go up into space if you're going to do a good job there, or any job at all. So the problems in, say, X-ray astronomy, where you might be trying to study the behavior of the emission right around a black hole, well, unless you do the observing in the X-rays, it's still going to be there, even 20 years later. So but you're right, fields change, and there are things you can do for less, especially when you're first, breaking through into a new area. So they're more modest projects, and NASA announced a few of them at the beginning of this year, and they're $20 million class projects, and so there's what we call small sats, and so these people proposed in 2020, they getting their start in 2021, they'll launch in 2024. So 4 years from proposal to launch is about as fast as you can do things in space. On the ground, it's only a little shorter than that, because if you're building a complicated instrument, there's the engineering, you have to put in the proposal first to get money from somewhere. $10 million doesn't grow on trees. And then you have a project manager. It goes on for several years. So it's really, you can't do anything in just 6 months. Just not possible.
And we've seen that in 2020 or 2021, SpaceX is kind of the big buzzword. Do you think that with space becoming increasingly private, and that with there being an increasing commercial interest in space, that means that, for example, the cost of manufacturing satellites, the cost of launch will go down? And do you think that'll make space a much more viable platform for astronomy than it used to be, even say like 5 or 10 years ago? Or will that not affect observational astronomy so much?
Well, it does lower the cost to get up into space. And so NASA does some research in rockets, but they are not allowed to build their own rockets. And this was a law passed in the 60s. They have to contract to industry. And they can also contract with industry to develop the technology and to help them along. So, for example, SpaceX and some other companies got, twiddle $500 million to develop their stuff. So, Elon Musk wasn't just doing it out of his pocket. But NASA and everyone else considers it's money well spent, because what they were looking to do is exactly what they said. You said they were looking to decrease the launch costs to get up, and they've done that. So the cost to get into orbit, low Earth orbit, or some more distant orbit, is significantly less than it used to be. I'm not sure if it's a factor of 2, but it's something like that. So if that was most of the cost of a mission, then yes, astronomy in space would be much more viable. But it's not most of the cost of a mission. It's 20%. And so if you make it, instead of 20%, you make it 10%. Well, it helps. It definitely helps. So the Explorer that I'm working on, you have to identify a potential launch vehicle and show that your satellite and will fit in the fairing and things like that. And so we have a SpaceX rocket, that launcher that we've identified as the launch vehicle. And that just sets the cost and sets the parameters of what you're going to build. Now with so NASA certainly isn't working on promoting tourism in space, but since since it's companies who build the rockets and all sorts of launch vehicles, they can do whatever they want within limits. We have an understanding of what sort of orbits, what's going to be in what sort of orbits. So no one would be allowed, well, even though we don't have rock solid treaties, no one would put a polar orbit at the same altitude as the space station, for example. and you'll just get collisions. So there are different heights. You have different types of orbits. And, there's, it looks like space tourism is happening. It's kind of fun to see. My family told me I cannot go up into space. But yeah, so it's, and, the big thing that Elon Musk wants to do is he wants to go to Mars. And he wants to be able to land nicely on Mars. So his big thing with the new launch vehicles is that, and one way of reducing costs, is the first stage, he, instead of just having it land in the ocean and sink to the bottom, he lands it on a platform. And this is good economics, you can reuse it, but also it's preparation for landing on Mars. And they've gotten pretty good at landing these things. They're not 100%, but they're doing pretty well.
Yeah, they definitely have. And it's interesting to see how it's developed. Initially when SpaceX came out with this idea of going to Mars, the goal was go to Mars. But now with the Trump administration, there's been a lot of focus and a shift in NASA's perspective on going to the moon first as a quote unquote launching pad to Mars eventually.
Yeah, so that's the so the NASA plan, which grew up with, really started with the Bush administration, but got to move forward with the Trump administration, and also it is to have. So the space station we have is fine, but it's in low Earth orbit, and going from there to some other place still means you have to escape most of the Earth's gravitational field. Mm-hmm. So why don't we have a space station that is in really relatively low gravitational field, much further out, that from which you can launch to go to other places. And that's this gateway that NASA has been talking about. So we have this moon to Mars thing, and some of these things are remarkably accidental. So somehow during the Bush administration, they got wound up about China going to the moon and said, well, we have to go back there. Okay, well, and that may happen. We may go back there and establish a base. And, there are parallels with exploring the South Pole. So at first, the big push was to get to the South Pole. And then once that was done a few times, everyone forgot about it. And then 50 years later, people thought, let's establish a base down in the South Pole. And so we have McMurdo Base down there. So this is the moon equivalent of McMurdo Base. And, am I a big supporter of it? Well, not really. It depends on what your motivation is. If your motivation is to get used to living in space, then yeah, it's a good thing to do. Because you'd like to do this not just on the moon, but maybe on other planets, on spacecraft going to other locations. But it was one of these things that really got wings due to, one speech that was never followed up on. Someone got to Cheney and had them, release this thing. And then, it eventually got some life breathed into it. The problem with it, though, is that they never provide the money for it. So, if you ask, okay, suppose we want to go to the moon, we want to land, build something, we're going to do it in the next decade, how much money would it take? Well, you're talking about, $5 billion a year. Mm-hmm. And the that's not chump change, because the NASA budget is 22 billion a year. So that's a very big augmentation. Congress doesn't like such big augmentations. So what they did is they found 1.4 billion to add to the budget in the last several years. That's not really going to get you anywhere.
And is there an astronomical interest in the moon? Would it be helpful to put satellites or telescopes or observatories there?
Not really. Well, there's one thing that you could do. You could put radio telescopes on the far side of the moon, and then you're not dealing with radio interference, and there are a number of projects you can do from there. And this friend of mine carries that bullhorn and uses it every time he can. But in general, when you're on a solid body, there's vibration, there's dust, there's all kinds of stuff. And if you're just in space, you can choose better locations that don't have those problems. And so, yeah, there might be a few niche things you could do on the moon in terms of astronomy. But in general, it's more that you would be looking into how you could live on such a place. One of the things that you hear about is space mining, but the former head of science at NASA, who's Len Fisk, who's in the engineering school now, said that he wants to do this calculation. If you sent up the space shuttle empty, filled it with gold, and landed it again, how much money did you make? And it turned out you would have lost money. And gold and platinum, iridium, they're about as expensive as metals get. The rare earths, they're actually pretty cheap relative to gold. So, I don't think you'd ever really do space mining unless you were using it to put on a spacecraft to go to another world. For example, you didn't want to carry up a lot of gallons of water because it's just expensive to get up there. And instead you find a comet or some little thing and you melt it down, and that's your water.
Yeah, it makes the most sense to, like, in the future, like I know SpaceX and other private companies in discussion of, sending men and women to Mars would be, utilizing the in situ resources, whether that be melting down the Martian regolith or even the lunar regolith to build habitats, or even, somehow tapping the atmosphere to somehow make rocket fuel.
Oh yeah, once you're there, once you're on Mars, there's a lot of stuff you can use on Mars. Yeah. It has an atmosphere, for example. The moon, not so much. Mm-hmm. And but there are just so many things that go wrong.
It's very interesting. But it reminds me of when, originally when we went to the moon, the John F. Kennedy quote: "We do it not because it's easy, but because it's difficult." But in relation to your research, I know you said that no, we can't put observatories on the moon. So I was thinking, maybe we could put some type of X-ray observatory, since we don't have the atmosphere around the moon. But you mentioned, I wasn't even thinking that with the vibrational or the dust component on the moon, that wouldn't really be possible.
No, it would work. You could put an X-ray telescope on the moon, but it'd probably be a lot cheaper to just put it in space, because you don't have to land it, set it up. You just send it ready to go.
And so you mentioned developing an Explorer mission, or working on a proposal for later this year. And so I was hoping you could kind of maybe describe to us what that mission is specifically, but also what your broader research is here at the University of Michigan.
Okay. So usually interested in the gaseous content of galaxies, clusters of galaxies, and the space between them, the intergalactic medium. And the reason for it is that the universe really started off early on as a combination of dark matter, which is most of the gravitating matter, and normal matter, which was all gaseous to begin with. And actually, most of the normal matter is still gaseous today. So you find it in these giant regions throughout clusters of galaxies. You find it as a very extended atmosphere around the Milky Way and other galaxies. And its properties help tell you how the galaxy formed and how it has evolved. So the gas comes in different temperatures, different flavors, but probably about half of it is very hot. And by very hot, I mean about, within factor 2, about 1 million degrees around the Milky Way. To see this gas, you can try to see it in emission or absorption. And the emission is easier to see near the galaxy because the emission is proportional to the square of the density, so it lights up in dense regions. But but that may not be most of the mass. The absorption, on the other hand, is a linear tracer of the mass. It's just as proportional to how much stuff you have out there. So if you can measure the absorption lines from through the Milky Way, through the halos of other galaxies, through the intergalactic medium, you can say how much of it is there, and what temperature, and what its composition is, what made it. So those are the issues that I'm most interested in.
And have you? Oh, go ahead.
Yeah, we've done what we can with, say, the data at hand. And there are still additional observing projects I have that get approved. But we can see the X-ray emission and absorption from the Milky Way. The absorption is not bad. The emission is not bad to do. We have a lot of data on that. The absorption is very challenging. We have just a few good directions and a couple dozen more directions where the signal is wanting. So what this project will do, and then we have essentially no absorption lines beyond the Milky Way. What this will do is this Explorer mission called AUKUS, is it will improve our ability to detect absorption lines by a factor of 50. It's a big improvement. And this will put us over the edge. We'll be able to detect absorption by the Milky Way in hundreds of different directions. We'll be able to detect halos around other galaxies, probably groups of galaxies, and maybe even the intergalactic medium. Mm-hmm. So and we'll know something about the motion of these things. So we will go from barely being able to scratch the surface to really a watershed set of observations that will change the field.
Interesting.
How did you get into studying that? Because I think a lot of people who either are starting off studying astronomy or who are not, or who, don't pursue it as a career would, they understand that in college you take some classes and in grad school you take some classes and you learn some things out of textbooks. But how did you go from this is a textbook on one particular subject to deciding this is the subject that I want to get to know better than there exists a textbook for? How did you end up making this as your area of research?
Well, it was somewhat accidental. Today it would be easier. I could say, okay, here's the 2020 Decadal Survey report, and it's hundreds of pages. Read the science stuff, and get an idea of what's going on. And in support of this Decadal Survey program, people put in what they call white papers about, here's some great science. and this is what could be done. And I wrote one of those papers as well. And they're not long; they're 6 pages, 7 pages, and there are actually a few hundred of them. And so you can survey not only what we know, but what we could hope to know in the coming years. And you may decide that, what I really want to move into is this, that, or the other thing. In my case, it was, and there are downsides to some of this too, because some of these things require big collaborations. It's not, and so do you want to be involved in a collaboration of 300 people or 50 people or whatever it takes? The smaller ones I like more than the bigger ones. That's just me. But, these big collaborations can do things that are remarkable. So one of the, so there are a lot of surveys that are going on and have gone on, surveys of galaxies through the universe, surveys of stars. And they realize that to answer certain scientific questions, you need a large number of stars or galaxies or whatever it is you're looking at. And this isn't something that one person can do. So you get a team together and you get the resources. And we've seen that programs like the Sloan Digital Sky Survey, and there are a number of others, have just completely transformed the field. Now, one of the problems with being involved in a large group is they're doing great stuff. It's easy to get lost. It's easy to just become a cog in the machine. How do you rise above that such that you are making your own mark and doing something interesting? And that's a question that anyone moving into a new field needs to ask. Can I effectively become part of this, or do I have to join this big team? And what are the pitfalls of doing that? In my case, I was, as a graduate student, I was listening to a colloquium by this fellow who's invited to give a talk. It was on X-ray astronomy. It wasn't something that was commonly talked about at that time. It was a new field. It was a decade old at that point. And I found out that a large fraction of the gas in the Milky Way actually could be quite hot, could be this 1,000,000-degree range. I thought, wow, this is amazing. These other areas had become a little staid in terms of the studies, but this was an entirely new thing. Now, it turned out that even though I didn't realize that at that time, strategically, that was a good decision. That is, it was a new opportunity, it was an expanding field, and I could get involved at early stage, and did so. And we were just launching the first imaging observatories in X-rays. So, those things came together pretty well. So without really fully understanding what I was doing, I was being opportunistic, moving into a new and interesting area without fully understanding that all of the implications that go along with it. And, you do something and then maybe you think you'll move on. And I have moved from one field to another. But it's a little like those movies about a drug dealer who tries to go straight and they bring him back for one more gig. There are always some projects that they want me to be involved in because I worked on it, a while ago, and might have something to say about it, and that they're actually fun. So it's okay.
And I think this it is quite shocking to hear, if you heard it for the first time, that gas in the middle of galaxies is at 1,000,000 degrees, considering that it's pretty far from suns and other heat producing objects. So how does it get so hot, broadly speaking?
Yeah, it's well, it doesn't get hot just by shining light on it. it has to be shocked. So this is a technical aspect because of the radiative cooling increases as you go up in temperature. So if you slowly tried to bring it up to 1,000,000 degrees, it would never get there because it would cool back down too fast. But if you have, say, a supernova that blows up and the shock wave moves out, the shock wave, as it passes through, kicks up the temperature behind the shock. So the temperature ahead of the shock may be 100 degrees Kelvin, and the temperature behind the shock may be 4 million degrees Kelvin. So shocks from supernovae do it. Another thing that happens is that gas can fall onto galaxies. And well, the galaxy has its own atmosphere that's been there for a while now. And when something falls onto it, once again, there's this big accretion shock. And it just happens to be that the characteristic temperature of most galaxies is that it will heat, the gas behind that accretion shock will heat up to 1,000,000 or a few million degrees. So it's kind of a natural, if you were to calculate the characteristic temperature of most astronomical systems, stars, galaxies, it would be in this million or multi-million degree range. It's an odd thing. And the reason, the sun's a good example. The sun's 15 million degrees, but that's in the middle. And then you put gas around it that's opaque and an atmosphere, and it brings it down to 6,000 degrees. But its characteristic temperature really is more like 10 million degrees. So.
And then after your time as a graduate student and then your postdocs, did you go directly to the University of Michigan as a professor or as an assistant professor, or how exactly did you get to where you are now?
So the usual transition is you go from being a graduate student to a postdoc, and then after 1 or 2 postdocs, you transition to a faculty position of some sort. And so I did that. I was a postdoc and then a research scientist at Columbia and New York universities. I then took on a faculty position at or lab position at the National Radio Astronomy Observatory in Charlottesville, Virginia. And from there, I came to Michigan in 1989. So there was.
And then was your time at the National Radio Lab, was that because we were talking about X-rays and now it's a radio lab? Is it because they dealt also with X-ray observations, or were you at the time interested in?
I was interested in a bunch of different things, and it was a period of time when the observatory there said, we shouldn't just have radio astronomers here. We should have a wider range of people to talk to. And so it was during that Let 1,000 Flowers Bloom period that they brought me in. And then I think that period passed.
And how did you make the transition from being a scientist to being a scientist and a teacher effectively? Because I think, clearly teaching is a skill that's somewhat separate from just knowing your stuff well. They're obviously connected, but there is also a big difference. And there are people, and I know this personally because I've sat in their classes, who clearly know their stuff, but kind of struggle to teach it. And in the case of scientists, for example, the traditional path to becoming a professor involves no teaching for a long time, and then they just kind of seem to throw you back in. Did you find that transition easy to deal with, or was it a big difference from what you had been doing?
Yeah, so I would say that teaching is, as a craft, is not taught to faculty at colleges and universities. They may pick it up, but so one is taught how to do research. But I have really 3 jobs. I do research, I do administration, and I do teaching. Those other 2 jobs, one isn't taught. You're just expected to pick it up And how do you pick it up? Well, you do what your what your teachers in college and graduate school did. And so that model actually traces back to the beginning of universities, where no one really had enough money to buy their own books. And so it was almost a transcription service. Professor would be up in the front reading the book, maybe explaining some things, and you'd write things down. And in a lot of classes, that's almost still how it goes, right? It's the presentation of material, you just sit there, you take notes, that's it. That is, in K through 12, that's considered an antique model of teaching. It's a very old methodology. And it has great failures. So one of the problems is that, as was noted at some of the very top institutions, bringing in the top graduate students around in the US, is that these people couldn't think very well. And they were good at a few tasks, but they weren't being educated to be scientists very well, to function as scientists. So that's something I've become very interested in. How does one learn better? How does one become engaged in one's own education? That's somewhat, and so that involves a very different way of teaching that is interactive, where the students are involved every day in the class. Another part of that, which is rather hard to do, is that, how does one develop critical thought and the ability to do the calculations that scientists do every day? And that's something that I have been trying to bring into my class. Some of it I understand how to do, such as the calculations, the approximations. Some of it I understand what needs to be done, but I don't understand how to teach it very well, such as having students come up with hypotheses given a set of information. And so, my teaching has evolved a lot, and I spend a tremendous amount of time developing materials for class. That's okay, as long as I get to teach the class again and get to refine them, and that is happening. So so my idea about how to teach has changed a lot, and although it's not as widely used as I would like, even within my department, which is pretty advanced in their ideas of education, one can already see the differences and the improvement in, say, the undergraduate and graduate programs, in terms of students being able to think more like scientists. But it has been a slow process. And, but, if you have type A individuals and you tell them to do a good job in this, then the other thing, they will. So.
And do you see COVID and the kind of transition of everything being online having an impact on the university education system, or even astronomy research for that matter?
Well, it's somehow we're getting through it. Mm-hmm. And even the research parts. I thought the research parts would really suffer, but actually it hasn't been as bad as I thought it would be. What's really missing from, I think that if you work really hard at it, the class that you do via Zoom can be a good one. But I think what's missing is the relationships and the connections between students and the faculty. So, for example, when I would usually teach, I would say, okay, I want groups of three. Just find your neighbors and talk about this issue. And I could walk around the class and I could see if things were going south or if they were making progress. I could make comments. And that's more or less impossible to do with Zoom. And whenever I show up in a room, all conversation stops. So I don't do that anymore. There is the university experience. There is the experience of living outside of home, learning how to have relationships, both professionally with faculty, have friendships. So, all of those things are lost with remote learning. And that's too bad. One of the things that actually might be positive that come out of this is that I and others, everyone in my department has to travel a certain amount. You have an observing run at a telescope. You have to go to a conference. You're you're doing a site visit that's somewhere else. And what you'd normally do is you would find a faculty member and you'd hand them your materials and they'd run off and teach for you. But with now that we have all this experience with Zoom, what we could say is, okay, for these two classes, we're just going to meet remotely. We're just going to Zoom in. And, so I'm not going to ask someone to teach my class. And there are times where I'll have to, right? So be in a proposal review that's 8 to 6 in the day. But it opens some interesting possibilities.
And one thing we like to ask our guests that are professors at universities is advice they had for students, because a large portion of our podcast audience are students, whether it be at the University of Michigan or other universities studying physics, astronomy, or some type of a STEM field. And so do you have any advice for undergraduate students or even graduate students, or maybe even something that you weren't told when you were an undergrad or graduate student that you've kind of discovered or learned over the course of your career?
Yes. So there are, it's hard to predict what you're going to be doing. I work in fields that didn't exist when I was an undergraduate. And I'm certainly in places that I didn't expect to be, and doing advising in government. So you have to prepare yourself in general ways so that you're adaptable to these things. There are some technical things that I think are extremely valuable today. So learning how to program, and this probably means Python to most people. I think that's a very important skill set. Like I said, being able to think critically and being able to teach yourself new material are two skills that one should seek to develop in college, because you're going to have to be teaching yourself new things all the time once you get out. And often you're going to have to do things without anyone looking over your back very much. So, right now, you get a homework assignment, you do the assignment, you get partial credit for things. At some point in the, either in the academic research area or the business world, there's no partial credit. You just have to get things right almost all the time. So you have to develop ways of double checking yourself and doing things in a few different ways such that it all seems to make sense. And even if it's wrong, it must be close. And that's one of the things actually I try to develop. I try to do when I teach. But those are things that are very important. One thing that students usually don't do is they don't read enough about the fields they're interested in. And there's say in astronomy, you raise the question, well, how do you know what you'd be interested in? Well, yeah, you have to read about stuff. And these, for example, those white papers I mentioned, there's a lot of material out there these days, and it's free, it's easily available. And it may be in that, it may be in photovoltaics. You may say that I'm interested in being in the energy field or the global warming field. Where might I fit in? And there are a number of different angles that one can take. You know, there's a research part, there's a government part, there's a production part, and so you have to decide what you like and will this work for me? And you know, even though I do various government policy things, I wouldn't want to be involved in a lot of the political wars that have to do with energy. It would just, I feel passionate about it, so it would frustrate me a lot. But I work with people for whom it's like playing poker. They get a hand, it's a losing hand, they fold it, play the next hand. And so, you know, if you're trying to convince congressmen or groups or industrial groups to do this, that, or the other thing, do it. But then, you know, you're going to have to realize that you may be turned away, and it's not personal. You don't worry about it. And I've worked with people like that, and they somehow keep the big picture in focus as they move forward from failure to occasional success. So you have to know yourself.
And we thought that as an interesting last question, we always like to ask, what do you think, what are your biggest hopes for either your field in X-ray astronomy or astronomy in general? What are your biggest hopes for the field in, say, for the near future, say in like 10 years? What do you hope to see what you think is necessary to happen, that should happen?
Well, the biggest thing I'd like to see, although it's going to take more than 10 years, might take 20 or more, is to demonstrate that there are planets with atmospheres that can support life, and maybe have the biomarkers of life, such as ozone. And that's a big one. It's going to be a pretty tough business, but people are certainly working on it. And you know, as far as I'm concerned with this, the thing I want to see the most in the near term being this decade, is our ability to detect this hot gas and absorption on a regular basis. It would just completely open up a new field in astronomy. And I'm also hoping that international projects will become a little easier, especially with China. So, you know, I like couple of the things that they're doing. I certainly wouldn't trade the US astrophysics for Chinese astrophysics, but we can't do everything. And there are a lot of interesting things to do. You know, for example, the Hubble Space Telescope can do ultraviolet absorption, ultraviolet spectroscopy. It's not going to last forever. If we're lucky, it'll last another 5 years. There's nothing on the drawing boards of any country to provide us with that replacement ability in the ultraviolet. And then we'll just be, you know, so when you want to solve a problem and you say, you know, to do this, we really need some ultraviolet spectroscopy or imaging, and you don't have it. So there are countries that are, you know, looking for projects but don't necessarily have the technology. We have the technology, but it's not a high priority for us. But if you get together internationally, you can do more than, different groups contribute. Someone has to drive the bus, but you can have a number of countries contributing. And so I'm hoping that that sort of international collaboration works better in the future, especially with countries that have become challenging to deal with, such as China.
And would NASA be the facilitator for connections or international connections, or is there a larger organization that deals with astronomy between countries?
No, there isn't. It was so there's in Europe, there's the European Space Agency, which is all these European countries that contribute, and they have treaties, and that negotiates for them. For in the United States, for space projects, it would be NASA. For ground-based projects, it would be the National Science Foundation, or for some things, Department of Energy.
Okay.
So, for example, we are involved in expanding the gravity wave detection system, and the Department of Energy. Well, there's that's mainly a National Science Foundation, but yeah. So
I think those are great things to look forward to, whether it be the next decade or the next few decades, because I think finding, the possibility of life, even if, we find some past evidence of life on Mars, I think that finding atmospheres that could harbor life is definitely more of a statement, knowing that, the whole Milky Way galaxy could be teeming with life is a pretty interesting question that has yet to be answered.
Yeah, I think that, things are not looking great for Mars.
Yeah.
But it's close, and unlike Venus, you can land on it and travel around. And so that's why we do it, because we can. And there's still things to learn.
Yes. Yep.
Awesome.
Yeah. Well, thank you again for taking the time to be on our podcast today. We really enjoyed the conversation, and I thought talking about space policy and your research specifically was really insightful and interesting. So thank you again.
You're welcome.
Hey everyone, thank you for listening to this podcast episode. This is Michael.
This is Sam.
This is Tommy.
And this is Joe.
If you're listening to this on YouTube, make sure to like, subscribe, and share with your friends. And if you're listening on Apple Podcasts or Spotify, make sure to leave a review. All of the show notes can be found either in the description below or on our website. Thank you again for listening, and we'll see you next week with more Everything Astronomy.